Hello, this is Graham, and in this video we'll be talking about the different mathematical principles that go into robotics. So without further ado, threading. Threading is typically identified by two numbers, and those two numbers are the diameter and the threads per inch. The diameter can come in the form of fractional inches or as some whole number like 8 or 10. And those are on a different scale, kind of like gauges on wire. And the second is in threads per inch, which is, I would say, a more important measure of it, because if I were to take a 1032 bolt and try and put it into a 1024 hole, I would end up destroying the threads on both of the threaded areas, and I would have to redo the threading, which isn't always that enjoyable. Torque. Torque is found by multiplying force times the distance from the center times the angle between the distance and force vectors. In this graphic, you can see there's a force vector, a distance vector, and theta here is the angle between them. And ideally, you would want theta to be 90 degrees, because the sine of 90 is 1, and that is the highest value of sine that you can get. And if that's the highest value that sine can get, that means that that will give you the maximum amount of torque. So knowing the formula and that being at 90 and turning something tangent to distance is pretty cool. Let's say that the power in the shop went out, and Mr. Marcumbi, our fabrication lead, he needs to machine something still. So we are able to construct an 8-foot wheel, 8 feet in diameter. So let's say we live in a perfect world in which the freshmen who are required to push it in order to build their upper body strength don't get tired, and they understand that pushing tangent to the wheel is going to give us the most amount of torque. How much force would they need to apply in order to generate the 1.21 foot-tons of torque required to give the mill enough power? And of course, in this, we don't have any spare plutonium on us, so we'll have to use manpower. So I'll let you guys think up the answer, try and do it on your own, and then come back and I'll show you how to do it. Alright, so we know that torque is equal to force times distance times the sine of the angle between the two vectors. Now, since this is going to be 90 degrees, it'll be 1, so we don't care about it anymore. I'm sorry. And from this, we can say with confidence that force is equal to, torque times distance. Now, I apologize if my handwriting is atrocious in this, but we'll try and work our way through it. So we know that torque is equal to that our torque is 1.21 foot-tons. And we know that our distance is 4 feet, because that is the radius of our wheel, and that's what we want. So feet can cancel out there. Now we're just left with tons. But the problem with this is that we normally don't use tons. Normally, whenever we use force, it's in pounds. So we'll use what's called a conversion factor. And a conversion factor simply allows you to convert between different units. In this case, it allows us to convert from tons to pounds. So the tons here can cancel out, and we're left with pounds. And after multiplying everything out, we are left with force equals 205 pounds of force. Now, that's a lot more than the human body can produce. So we'll use something to help us out, and those are called belts. And the way that belts work is by applying a torque on one wheel, it will apply a proportional torque on the other. So in order to find that, you take the input torque, which we'll say is T1, and you multiply that by the ratio between the diameter of the driven wheel, which is, in this graphic, the larger wheel, and that's the wheel that is being moved due to the motion of the driving wheel. The driving wheel is what we are turning ourselves. We are putting force onto that, and therefore it will apply that force to the driven wheel, and that will generate a torque for it. So this practice problem, so we now have a wheel that is 32 feet in diameter, because the bigger we can make it, the better. And so now we want to know how much force would we need now, given this. So here, first, I'll let you guys do this on your own, and then you can come back to me whenever you think you've got it, and I'll show you, or I'll tell you if you got it right or wrong. Okay, so now we have this as our force, right? 605 pounds. Now, all that we really need to do in this case is we need to find the ratio and then divide it by that ratio. Because, because this will be the force that is outputted, I guess you could say. So we have, so our wheel is going to be, the wheel that we are turning is 8 feet in diameter. The wheel that will be turned by that, because of the pulleys, is going to be 32 feet in diameter, which means that it will be, that the output torque will be 4 times the input torque, meaning that we have to apply 1/4 of the force that we are currently applying, which is equal to 121.5 pounds of force. And that, my friends, is a lot more manageable. So we can take this one step further with gear ratios. And the gear ratios determine a lot about how certain systems go. It can change this. It changes the rotational velocity between gears, how many times it'll rotate in a given amount of time, the torque being applied. Almost everything that you could work with is dependent on these ratios. And to find the ratio, you take the number of teeth of the driven gear, which, as we said before, is the one being turned by the driving gear, or the driver gear, and then the driving gear is what we're turning. So in the case of this graphic, we have a driven gear with 75 teeth, and we have a driver gear of 25, meaning our ratio is 3, meaning that whatever torque is applied to this will be 3 times greater on this, it will be 3 times more on this, and the speed will be reduced by 3. So that's not the only kind of way you could set up gears. There's also what's called a planetary gear setup, and we'll normally see those in the form of versaplanetary gearboxes, and they are much smaller gearboxes than what you'll typically see in a lot of systems. And we only use them because it's just impractical to use them in certain places, and honestly, it can provide a lot more reduction, or I guess in some cases it'll provide more speed. But anyway, the output gear ratio for these are 1 to 1 plus the amount of teeth on the ring gear, which has its teeth on the inside of it rather than the outside, like most gears. And for versaplanetaries, that's always going to be 32 teeth. And you divide that by the number of teeth on the sun gear, which is this gear in the middle that doesn't have an axle. So since it doesn't have an axle, it's turned by these 3 gears on the outside spinning around inside the ring gear. And so another thing we can do is we can stack up some things. So if we wanted to find, if I were to turn the driver gear at a certain speed, the final driven gear will look like, in the case of this, will just be the ratio between the driver and the driven. That's the difference. The 2 wheels here in the middle, or the 2 gears in the middle, are the intermediate or idler gears. And those are either for increasing your distance or for getting the right direction you want. So in the case of this, since it doesn't really change much about the direction, it's most likely just for the distance that you'll get. And there's also compound gear trains, which work on multiple layers like this, and you can find the ratio between this and this, by multiplying the ratio between these 2 gears and these 2 gears. With this is your driving, this is your driven, this is a driving, this is a driven, like that. And so now that you know all of that, the last practice problem for this, the last practice problem for this unit, I guess we could call it, is this. So we want to use a motor to power instead of people, because people are unreliable and can get tired. Motors cannot. But the most amount of torque we can apply by a motor alone is around 2.25 foot-pounds of torque. But that means that we need to have a gear ratio of 54 in order to match what we need to put in. So we'll use a series of gears, and the gears that we have is an 8-tooth pinion, which will be the first gear that you put in because that is connected directly to the motor. And the other gears we have are 12 teeth, 24 teeth, and 36 teeth. And so I'll let you come up with your method for this, and you can, whenever you're done, you can replay the video or resume the video, and you can see how I went through it. All right, so now that you're back, so we'll start out with our 8-tooth gear, our pinion. I would then connect it to a 24-tooth gear. So now we have a gear ratio of 24 to 8, or 3 to 1. And that's good. That's what we want. Now the smallest we can do is 12, and that's okay. So now that we have 12, I'm going to do 36. That'll be 36 to 12, which is, again, 3 to 1. And then I'll do, I'm not going to bother with it, but I do this setup another time. So now this is going to be 12, this is going to be 36, and this is going to be 12. And so now we have from this one to this one, 36 to 12, which is another 3 to 1. And finally, 24. That'll be our final gear. And so now we have 24 to 12, which I'm just going to write here is 2 to 1. So now we can multiply all these together. So 3 times 3 times 3 times 2, which is the same as 9 times 6, which is 54. Awesome, we did it. We have now created a spinning wheel to power a mill, and we can use motors and gear ratios to keep a constant flow of power. So now that that's done, you can erase all of this and forget it ever happened. Now we'll go into electrical mathematics. So first thing you need to know about electrical systems is the difference between a circuit in series and a circuit in parallel. A circuit in series has only one path, as you can see in this. It goes around and back. It only has one way for current to flow. And since it does, it'll have a constant current throughout it, but there will be voltage drops depending on the resistance of components. In this case, since they are the same, they would have the same amount of have the same voltage drops. And the other way to set up a circuit is in parallel, which allows for multiple paths for current to flow, like this. And since it does, the current throughout the circuit will change depending on the resistance. So, and since these are the same thing, you just divide the total current by 2. And the voltage throughout it will remain the same, which is really just kind of neat, in my opinion. Another thing you'll need to know is a AKINERFON'S triangle. Now, the way that a AKINERFON'S triangle works, well, first I should talk about the origins of a AKINERFON'S triangle. A AKINERFON'S triangle was jokingly named after one of the teachers in our school that just couldn't remember this triangle. It's really called Ohm's Law's triangle. And the way it works is you have voltage on top, current, and then current and resistance. And if you cover up one of them, then you'll get the equation for it. So in this case, we have voltage covered, and so we'll have current, times resistance. If we cover up current, then we'll have voltage divided by resistance. And if we cover up resistance, we will have voltage over current. And that all works. But what is voltage, current, and resistance? Well, voltage is the work needed to, or per unit of charge to move a charge between 2 points. So this is expressed in volts, and at one point I'm going to refer to it in joules per coulombs, and that's just a unit of charge. Current is the rate of flow of electric charge past a point or region. This is measured in amperes, and I'll refer it at one point as coulombs over seconds. And resistance is measured in ohms, and it's a measure of the opposition to flow of electric current. So now we can get into some big boy math here. Kirchhoff's laws. So there's Kirchhoff's voltage law, which is for a circuit in series, and basically it says that your total voltage is equal to the sum of your voltage drops, which is equal to, which you can find by taking the total current, since it will always be the same, and then you multiply those by the resistance of each component along the path. And then those will give you your V1, V2, V3, add them up, and you get your total. In parallel, you use Kirchhoff's current law, which works similarly. The sum of currents along each path is equal to your total current, and you take the voltage total, divide it by the resistance of the component along the path, and you will get your I1, I2, I3, and you can add those together to get your total current. Resistance in parallel based on Kirchhoff's current law. So we can do this, and then we can say, well, resistance is equal to voltage over current. And so we can say that since we have this, we can divide total voltage from both sides, and we'll get this mess. You'll have the reciprocal of the total resistance is equal to the reciprocal of resistance of one component, and then you do that. And it's, I wouldn't say it's exactly a nice way to do this, but if you have the same resistance for each, it's much easier. But that's really all you need to know in terms of that. Now we can finally get to power. So power is equal to torque times rotational velocity, or voltage times current, and that's where the joule over coulombs and coulomb over seconds come in, because if you multiply those, the coulombs will cancel out, and you'll be left with joules per second or watts. Power can also be expressed in foot-pounds per second, and power is simply the amount of work that something can output over time. And the conversion factor for this would be 5,500 foot-pounds per second per 7,457 watts. And both of those are equal to 10 horsepower. So that's a good way to memorize it, is they're both equal to horsepower. So the first thing that I want you guys to do is think in your minds, how much power are we producing by spinning this wheel? Well, the motor is spinning at 1,500 RPM, and the gear ratios determine the rate at which the subsequent gears are moving. So you tell me, how much power are we outputting? I'll give you guys a moment to think about how to go about this and try and solve it for yourselves. And you can resume the video whenever you're done. Okay, so this one's going to be a lot harder to do, but we'll get through it. So the amount of torque that we are applying right now are here. We're applying this many pounds of force. This many pounds of force on 4 feet. So now we're at 605 foot-pounds per, or 605 foot-pounds. So now, since we know power is equal to torque times rotational velocity, and rotational velocity is RPMs. So we have this. And so now what we'll do is we will say that that is equal to 605 foot-pounds times 150. And I'm going to write it like this because it'll help us with conversions. But basically, we have it written like this. And this would be fine, but we also can't have revolutions, and we need this to be in seconds for it to work. So we'll use conversion factor, and we'll say 1 minute is equal to 60 seconds, which I think we can all agree on. And now for revolutions, we know that 1 revolution in radians is equal to 2 pi. 1 revolution is 360 degrees, or 2 pi. So now that we have that, we are left with foot-pounds per second. And when we multiply that all together, give me a minute here. So we have the 605 foot-pounds times 500 times 1500 times 2 pi, and we'll divide that by 60. This means that we are generating approximately 95, well, we can't do that, can we? 95,000 foot-pounds per second. So now the next thing that crosses your mind, and I think that will cross all of our minds, should we touch that wire that's being exposed? I'll just tell you right now that the answer will be no. You should never. But if our system is able to replicate the typical 110 volts from your typical American outlet, how many amps of current are we providing? Because it's amps that kill you. If there's too many amperes going through a current and you touch it, there's a good chance that you will die or sustain burns. So I'll give you guys a little bit to think about this and to solve it for your own, and then you can come back and I will explain it. Okay, so one thing we know is that this is our power right here. But if we're going to do this in amps, then we're going to need to convert this into watts. So that means that we have to take, so we do this, I'll just abbreviate this to foot-pounds per second, or 7,457 watts. Those will go away, and we will be left with about I can do better than that. 129,000 watts, or I'll just abbreviate it as kilowatts. So we have that, and we have our voltage. And we're dividing this because we know that power is equal to voltage times current. And if we want to find current, then we can just divide power by voltage. This also can be done with an AKINERFON'S triangle, but I normally don't do it because I find it unnecessary, but that's just me, I guess. And since we know that, we can do this math here. We'll say I equals is equal to 1.17 kiloamperes of current. Now that will be enough to burn you to a crisp. So I recommend you do not touch the nice shiny wire. And with that, we can conclude the electrical power and move on into fluid power. This will only be one slide long, and it's not going to be too hard, so don't worry. So the equation for pressure is force divided by area. So as you can see here, we have a force being applied onto a piston, the area of the surface area of the piston, and then you'll get the pressure inside of the system. So the way that engineers will do this is we'll say, or we'll use area in terms of diameter. So in this case, it'll come out to 4 times force divided by pi times diameter squared, because it's a lot easier to measure the diameter of something than it is to measure the radius. And for volume, you'll have the area of the face of the piston times the stroke length. The stroke length is just how far the piston moves up and down. You could say the height. And one thing that you need to know in order to do this problem is Pascal's law states that an external pressure applied to an enclosed fluid is transmitted uniformly throughout the volume of the liquid or gas. This means that the pressure inside this entire system is constant. The pressure in this is the same as the pressure in this, and the volume in this is the same as the volume in this. So, knowing that, we'll do our final practice problem. No celebration is complete without confetti. So we're going to use some pneumatic pistons, and we're going to make some really intense party poppers. So let's say someone stepped on a 3-inch wide pneumatic piston with 100 pounds of force. If there was a connected piston and we wanted to have that piston push up with a force of 40 pounds, how big would we need to make the piston? I need you guys to round up to the nearest inch so that don't have some crazy number like, I don't know, like 2.67 inches. So I'll let you guys do this, and whenever you're ready, you can resume the video and I'll show you how to do it. So now we can forget about all of that. So we have piston A. Piston A. Man, I promised you guys that I would get better at this, but I guess I was wrong. So this is 3 inches in diameter. And we're going down on it with 100 pounds, and this is connected I really do apologize, guys. And we need this. We have no clue what the diameter is, but we know that we need to push up with 40 pounds of force. So, in order to do that, we can say that the pressure inside of piston A is the same as the pressure inside of piston B. This is going to be piston A, and this is going to be piston B. So we know that the pressures are going to be the same, meaning that we can say force of A times the area of A, and I'll just go right into it, and 4 times force of A times pi diameter squared A is equal to force being applied, or being, I guess in this case, still applied to piston B and then we'll have diameter squared. Now 4 and pi can cancel out, thankfully. And we can take what's left of that and we can find the diameter of piston B like so. Diameter of piston B is equal to the square root. Let's see, so you would take that and you could flip both ends and then multiply by force, so we'll get the diameter of piston A squared times the force being applied on B divided by the force being applied on A, and then you find the square root of that and you'll get your diameter of piston B. So we'll replace all that and we'll come up with 9 square inches £40 and 100 pounds. Pounds will cancel out, which is good. And then we can say that we have the square root of 3.6 square inches, which when rounded up gets us to about good 2 inches. That, my friends, is the end of this mathematics lesson. I hope you guys enjoyed and learned something good.